9h, differentiating logarithmic functions. The rule for the derivative of log e of x is that when you derive it, it is simply equal to 1 on x. Even when I have a coefficient of x, such as k, it will still equal to 1 on x. We can actually figure out what this rule is or how it comes about using algebra. So remembering that what we're trying to find is the derivative, and although this is called f dash of x, another way to write it so that it is a little bit more understandable is that we are looking for dy of x. Also, so that it's in the same terms, instead of writing f of x equals to log ex, I'm going to write y equals to e of kx. Now, because we are trying to find out what the rule is for log e of x, we can't just differentiate it into the rule. We're going to try and use another rule that we know to help us get to this specific rule. And the rule that we do know is about exponentials. So I'm going to now transform this into my exponential. So the base is e. I'm just going to simply take that to the other side. That will be to the power of y is equal to kx. And then to get x by itself, I'm just going to divide both sides by k. Now, at this point, whilst I want to differentiate, I want to get dy by dx, I have x on its own. So what I can do is get dx by dy. So that's differentiate x in terms of y. Remembering that k is just a constant, so that will just stay as it is. And also remembering that the derivative of the e function also stays as it is. Nothing changes. So the derivative dx by dy is exactly the same. But I'm not looking for dx by dy. I'm looking for dy by dx. So how might I do this? Well, if I flip this fraction around, whatever I do to one side, I can do to the other. So I can flip this around, and that would equal to k on e to the power of y. Now, lastly, I want this derivative to be in terms of x, not in terms of y. So what I can do is substitute my original function of y. So that's dy over dx is equal to k on e to the power of log e k of x. Now, one of the rules in logarithms, although not spoken about as often, is that any base to a power with the same base essentially cancels out, and it leaves behind whatever that inside value is, which is b. So according to this rule, this will cancel out, and that will be k on k of x. The k's will then go ahead to cancel to give me 1 on x. From there, we can discover that the derivative of log e of x, or even log e of kx, will always equal 1 on x. This is a full set of rules, as explained previously. In general, f of x is equal to log e of g of x. So if we have a function on the inside, it will simply equal the derivative of the function at the top divided by the function itself. When we had kx as our function, so when it was g of x is equal to kx, well, the derivative of kx is k, and then g of x, so that would be k of x, was at the bottom, which is why those k's cancelled out. However, if I have another function, so say my g of x is something like 2x plus 3, the derivative of this is just 2, and that will be divided by 2x plus 3. So in this case, it does not cancel out as we had before. So that is why I start to see the derivative appear when I have more than one term, but when I only have one term, it will cancel out there. Let's apply this to some examples. Example 14, differentiate the following expressions. So all we want to do is recognize what is our inside function. Although I can see that the inside is just a 2, which means it will differentiate to 1 on x, if I want to use my general rule, which is always the easiest way to go about this, that is g dash of x divided by g of x. So that will equal 2 over 2x. The 2's will cancel out to give me 1 on x. Same thing goes for part B. So I want the derivative of the inside over the derivative of the outside. Now the inside is x on 2, so the derivative of the inside is going to be 1/2. The function on the inside is just x on 2. And now don't forget that this coefficient that's sitting out of the front is still hanging out there, so that's just times -5. 1/2 divided by 1/2 is just 1, so that will equal 1 on x times -5, which will equal -5x. Of course, if you can recognize that this is just a coefficient on the inside and that there are no other terms, this can be differentiated immediately to 1 on x and then multiply that by the -5. So you can go straight to this step here by recognizing that you don't need to do anything to the inside. That is different, however, to this over here. So now I can see that there is going to be a gradient on the inside and that function will be different. So the gradient of this inside function u is 5 and that will be over 5x plus 2. And of course, we're still going to multiply it by any other coefficient that I've got. So that will equal 10, 5x plus 2. Don't forget your notation as well. This case, it looks a little bit different. So first thing I'm going to do is I'm just going to take x to the top so it looks like an appropriate type of function to be able to derive. So this will be 3x to the power of -1/2. Remembering that what we are doing with logs if we have more than one value on the inside is that those values are multiplied. And in order to multiply two inside values, so if we have log AB, that means that's log of A plus log of B. So we must separate them in order to get rid of this power so that we can differentiate it appropriately. So that will be log E of 3 plus log E of x to the power of -1/2. Now what I can do is take this power out the front, remembering that log e of 3 is just simply a number. So if I continue with my notation, remembering I haven't differentiated yet, so that will be -1/2 log e x. Now when I go ahead to differentiate this, remembering that log e of 3 is just a number. So when you differentiate a number, it cancels out. So that will be gone. And now log e of x differentiates into 1 over x, and that is multiplied by the coefficient of the whole term, which is -1/2. So that will be -1 on 2x. Same idea goes here for part E. Before I can start working on it, I have to transform it into a form that I can actually use. So that's to a power of 1/2. I'll take the half out the front. Using my rule, I know that when I differentiate log e of x, that's 1 over x, or when I have a function on the inside, that's equal to g dash of x on g of x. And of course, I've got my coefficient out the front as well. So g dash of x, the derivative of this inside is just simply -3, and that's over the function itself. So that will be -3 over, you can expand this 2 straight away, so that will be 4 minus 6x. Some more examples. So first thing I can do is take the 1/3 out the front. Same rule applies. Coefficient remains as it is. That's multiplied by g dash of x over g of x. So g dash of x is the derivative of the inside. The derivative of the inside in this case is just 1 over x minus 1, and then we can simplify this. You can leave it factorized or expand it. It won't make a difference. For part G, again, power comes out the front. So this time this will be 6 log e, 2x minus 1. The coefficient remains multiplied by 1 on x, but of course we have an inside function, which is our g of x. So that will be the derivative of g of x on the top divided by g of x itself. So that will be 2 over 2x minus 1, which will be 12 over 2x minus 1. Last one, again, if you can recognize from our log laws that when I have two values being divided, that's the same as saying log of A minus log of B. So that's what I'm going to do here. I'm going to rewrite this as y equals log e of 2 minus log e of 2 minus 3x. So I'll just separate that. Now log e of 2 is just a value. So when I differentiate this, that will cancel out, that will go. And that will leave behind, first of all, a negative multiplied by the derivative of the inside by the function itself. That will be negative times the derivative of the inside is -3, and then the function itself is 2 minus 3x. So a negative and a negative makes a positive, so that will be 3 on 2 minus 3x.